Today's video is on chapter 12, which is on fluid dynamics. So in chapter 11, our fluids were at rest, and we talked about things like Archimedes' principle and Pascal's principle. But in chapter 12, we've got our fluid moving. So when a fluid moves, the flow rate equation applies, and it is a byproduct of the equation of continuity. So that says that within a system, your flow rate is constant throughout the system. And if that's the case, we can write it in this mathematical form. So Q would be the flow rate, and it would be equal to the mass of fluid passing a certain point divided by the time it takes it to pass. So it would be in kilograms per second. But mass is the same thing as density multiplied by volume. So we would have density times volume divided by time. But volume would be cross-sectional area times the length of the height of the object. And if you look at that, a distance, L, divided by a time would give us a velocity. So we can take our original flow rate equation of mass divided by time, and it converts into density times cross-sectional area times velocity. So density would be in kilograms per cubic meter, cross-sectional area would be in meters squared, and velocity would be in meters per second. So what we end up with is that rho AV is the same throughout a fluid, even if you change the diameter. So rho 1 A1 V1 is going to be rho 2 A2 V2 if you've got a pipe of variable diameter. But suppose that we let our densities be the same number. Maybe your fluid is incompressible enough that it maintains some integrity. So the densities would cancel out and we'd be left with A1 V1 equals A2 V2. Why is that significant? Well, let's look at our pipe. If you have a pipe and it's wide at one end and narrow at the other, the fluid increases in velocity in the narrow portion. So if A times V on the left end is true, then A times V on the right end has to equal it. And if we make the area smaller, then the velocity has to go up. If the area is smaller, the velocity has to go up. You have seen this in your daily life. If you take a garden hose and for some reason the little spray attachment is broken, but you're washing the car and you want the water to come out a little faster, you put your thumb over the end of the hose. And what that does is narrow the opening, and that makes the water flow out faster. Or if you've been rafting or canoeing, when a river narrows down, maybe there are some rocks in the water and it narrows the river, the water flows faster because the cross-sectional area has been reduced. So narrow the opening, it will increase the velocity. Enlarge the opening, it will decrease the velocity. Let's look at Bernouilli's principle. So with Bernouilli's principle, it says that in a fluid, a high velocity is associated with a low pressure, and a low velocity is associated with a high pressure. This used to just drive me crazy until I thought about, well, what is pressure? So suppose you are moving your hand along a tabletop. If you press down very lightly and exert a little pressure, you can move your hand quickly across the table. But the harder you press down, the harder it is to move across the table, so the slower you travel. So high velocity goes with a low pressure, low velocity goes with a high pressure. What's really cool about this is it is one part of providing lift to any sort of a wing shape. So we can look at, this is a cross-sectional area of something shaped like an airplane wing. So airplane wings typically are more rounded at the top and flatter at the bottom. So the air is coming from the left-hand side. As it gets split because of the wing, the air across the top has to travel a greater distance. And in order to do that, the speed actually increases. So the air across the top goes faster, but we've already said high velocity, low pressure. And the air across the bottom travels a shorter distance, so it'll have the higher pressure because it's got the slower velocity. And with a boat, the curve of the sail, that's what this is, an overhead view of a boat with a sail on it. So the black represents the sail. And again, the wind splits across, it goes faster on one side than the other. So you've got a pressure differential. And on the side where it's going slower has the larger pressure, and that forces the object to move. Let's talk about some other applications. Let's look at lift in a straw. So here we have my little blue glass. I was not very creative, and it's got fluid in it. And now we have my straw, and I am sucking up on the straw. So when we do that, what we have is a high velocity and what kind of pressure is that going to give me? That's going to give me a low pressure. So by sucking on the straw, you make the air inside the straw move quickly. It has a high velocity, so it exerts a low pressure. So we have a low pressure pushing up because the air is moving up. We have a low pressure, and we have a high pressure. Yes, the velocity, I guess we're showing, this is really the velocity, but there's a low pressure inside pushing down on it. I ought to insert, oh, come on, a little short arrow for a low pressure. And in fact, let's see if we can change the color and change the color. So we've got the low pressure pushing down, and we've got the high velocity going up. Because you've sucked on the straw. And the outside, what we have is high atmospheric pressure. I guess I need to move that over just a squidge. High atmospheric pressure. So we have high atmospheric pressure pushing down. And so the high pressure pushing down is stronger than the low pressure inside the straw, so the liquid gets pulled up the straw. It's forced up the straw. If we blow down across a piece of, if we blow across a piece of paper, so with this, what you do is hold a piece of paper straight down, I'm sorry, straight in front of you by the edges. You can see she's holding the edges. And then if you blow across it, what will happen if you blow fast enough, the air, notice her mouth is above the paper. If you blow, the air across the top is going fast, the air across the bottom is going slow. Low pressure on the top, high pressure on the bottom forces the paper up. And we'll try to do this demo in lab. We'll try to do the demo in lab. Suppose we blow down between, oh, I'm sorry, here's the graphic that shows this. So high velocity of the across the top gives you a low pressure, lower velocity across the bottom gives you a higher pressure. The high pressure pushes the paper up. Suppose we blow down between two pieces of paper. If that's the case, high velocity going between them equals a low pressure. So we've got a low pressure between. And then on the outside, we have a low velocity, so there's a higher pressure. So what happens is you've got a high pressure pushing in on the left and a high pressure pushing in on the right and a low pressure in the middle, and the two pieces of paper will actually come together. And so we will do this in lab. Shower curtains billowing in. Maybe you've been lucky enough that you've never been in a shower where you turn it on and suddenly the shower curtain sticks to your body. I've found this especially at camp. Seems that the camp showers are too small, and I don't know, the shower curtains are cheap. What can I say? So here is our shower pan. Here's our shower head. The blue water is trickling out. So if the water comes out fast, you have a high velocity on the inside and a low pressure. So we've got a low pressure. On the outside, the air is moving slowly. So it's got a low velocity and a high pressure. And the end result is that the higher pressure on the outside forces the shower curtain, which is this green squiggly thing, forces the shower curtain to billow in towards you. How do you fix it? Well, if you take this shower head and you adjust it so that the water points more farther away from the shower curtain, that'll stop it. Or if you can turn on the water so it doesn't flow quite as fast coming out of the shower, that will also stop the shower curtain from billowing in. So how about cars being pulled in toward trucks when they pass on the highway? I have a small car and normally it's not a problem, but sometimes when a truck is passing me or I'm passing a truck, I feel sucked. So let's look at what's going on when the two are side by side. So you have the truck and the car next to each other. The air in between gets narrowed. So in front of us is wide. The gap between the car and the truck is very small. That narrows the path and that increases the velocity, which decreases the pressure. So the pressure between is reduced. That means the pressure on the outside pushes in. The truck is big and heavy, and you can push on it and it's probably not going to move. My little Toyota Corolla is lightweight and it gets sucked in. So it's the difference in pressures. And that gets us to Bernoulli's equation. So if you have a pipe of variable diameter and variable height, then this relationship is true, that the pressure at one end of the pipe plus the density times the velocity squared of the fluid in the pipe divided by 2, plus the density times little g times the height of the pipe. All three of those things added together will equal those same three things at the other height and other diameter and other velocity. So P is pressure, V is velocity, Y is height above the ground. Where do you see this? Well, when you're designing plumbing for a house, you maybe haven't paid much attention, but the water usually comes into your house down at ground level. If you've got a crawl space, you can see where the pipe comes in, or perhaps you have a basement and it's easy to see where the water pipe comes in. And then it has to come up to the first floor and go to different places like the toilets and the kitchen sink and the washing machine and the shower. But if you have a 2-story house, not only does it have to cover the first floor, but it has to go up to the second story. And not all houses were designed to accommodate that. I had a friend with a house that had a bathroom on the second floor, but you could hardly use the bathroom because there wasn't enough water pressure to get the water to go that high. We are not going to calculate with this equation. I wanted you to see it. What I think is cool about it is that rho v squared over 2 reminds me of the kinetic energy equation, mv squared over 2, and rho gy reminds me of the potential energy equation, mgy. So it's easy for me to remember. If you think you're going to need this equation for a standardized test and you want some help with it, I'm happy to help you. There's an example in the book, and here's another example you could deal with. In an equation like this, with all those different variables, if they ask you to find two different variables, you have to have two independent equations. Two independent equations. So to do two, you would need to know Bernoulli's equation, and you'd need to know this version of the flow rate equation. And that finishes what we're going to say about this chapter. In the next video, we'll talk about chapter 13.